Hello everyone, my name is Sawyer Keller and I'm a technical sales and manufacturing engineer with LaCroix Precision Optics in Batesville, Arkansas. Today I will be presenting to you designing for manufacturability with fluorides and other high expansion materials. This presentation will mainly pertain to SFPL 51, 53, and 55, along with SFPM2 and SFPM3 from O'Hara. It will also include MPK51, MPK52A, and NPSK53A from SHOT. This presentation is applicable for other high expansion materials which are not listed here, but for the most part these materials will be the ones we will focus on throughout the duration of this presentation. As a general overview, we will discuss the risks and challenges which arise when manufacturing with fluorides and other high expansion materials. I'll provide you with some details as to why these materials are susceptible to said risks and challenges. We'll discuss these risks and challenges and how they can affect your project cost and timeline. I'll give you some methods of design that you can use to minimize these risks and challenges, and then I'll provide you with some general tolerancing guidelines for working with these materials on your future projects. So as I said, fluorides and high expansion materials pose quite a few risks and manufacturing challenges. These risks mainly include the risk of staining, the risk of fracturing, the risk of physical damage or poor surface, the ability to hold center thickness tolerance, and then uncertainty caused by variations in form. So the first risk is the risk of fracturing, and this is definitely the most critical risk. So the risk of fracturing is caused by the large coefficient of thermal expansion that comes with these materials. So basically these materials expand unevenly, which causes a stress differential to be generated in the part. And what I mean by that is for all non-planar optics or optics which are not windows, there are portions of the optic which are thicker than others. Just say for example we have a biconvex lens. The center of the lens will be thicker and the edge of the lens will be thinner. So with the coefficient of thermal expansion, the amount of expansion is directly related to the amount of material present. Therefore, for that biconvex lens example, there will be a larger amount of expansion in the center of the optic and a smaller amount of expansion at the edge of the optic. So this difference in expansion or non-uniform expansion throughout the optic will cause internal strain, and if this strain is too high, it can push the material past its yield point, in which you can have a partial fracture or you can entirely fracture the optic. The main high-risk processes for potential fracturing are both first side and second side polishing. In these processes, there is a large amount of heat generated due to the friction between the polishing pad or pitch and the surface of the optic. The cleaning process, the optic has to undergo a transition from room temperature to a cleaning solution at an elevated temperature, and this transition can be pretty abrupt, which can thermally shock the optic. These optics can also be cleaned with cleaning solutions that evaporate very quickly, which will quickly cool the surface of the optic, again causing thermal shock. The coating process will require that the temperature of the optic be elevated from room temperature to a fairly significant temperature for the thermal evaporative deposition process. And then the blocking process will require that the optic at room temperature be placed in contact with a hot metal tool with hot blocking pitch that is localized to a specific area of the part, which can again cause a stress differential. Next, we have the risk of staining. So the risk of staining, along with a few other risks that I'll mention momentarily, are not inherent specifically to high expansion materials, but they are inherent to the materials listed on the title page for this presentation. So for these optics, they generally have a very poor chemical resistance. They do not react well with aqueous acids or phosphates, and some do not react well with water, or at least they do not react well with humidity at an elevated temperature. So the high-risk processes for staining are mainly second side blocking, because as we said, a polished surface of the part will be in contact with a blocking pitch at an elevated temperature, along with moisture in the environment, which can potentially cause stain. And then in a first and second side polishing, many of these materials do not react well with the actual polishing compounds themselves. So during the polishing process, it's definitely necessary for these materials to be in contact with these compounds, and it is not an issue. But if these compounds are not immediately cleaned from the optic as soon as it is removed from the polisher, it can definitely cause stain to form on the surface. And we also see a risk of staining in long-term storage. And basically what we see there is that these optics, if their surfaces are not coated, during long-term storage, especially here in Arkansas, where you can have elevated levels of temperature and humidity, you can see, and we do see from time to time, that we may manufacture an optic and the surface be pristine. Then we place it in storage and say come back a year later, and there is potential that there can be stain that has formed on the surface solely while it was sitting in the shelf in our storage buildings, just due to the elevated temperature and humidity. Next, we have the risk of physical damage or poor surface. So this risk is due mainly to the fact these materials are generally exceptionally soft with very low abrasion resistance. Because they are so exceptionally soft, they are definitely intolerant of abrasions and physical damage. By that, I'm generally referring to scratch and digs. And most definitely during the manufacturing process, these optics often have to be physically handled in order to remove them from the polisher, load them in the polisher, move them into cleaning trays, the hand cleaning process, the inspection process. And during all these processes, they are very susceptible to, if the operator has a small piece of dirt potentially on their hand, or they have a small shard of glass that, say, came off the edge of the part, it can definitely scratch the surface. They're also very susceptible to, if you place a convex surface down in a tray in order to transport the parts from one manufacturing cell to another, they can very easily be scratched by the bottom of the tray. These materials also have issues with loading up polishing pads. So again, because they have such a very low abrasion resistance, as soon as you start polishing, the material can be removed and it can get clogged in the pores of the polishing pad. And as you continue polishing, you are continually dragging this material back over your polished surface, which can continually induce blistering or scratches into the surface. So your high-risk processes for physical damage or poor surface are mainly first and second side polishing, again because the polishing pad can get loaded with that old material, along with all handling operations after first side polish. So as soon as a polished surface is present on that part, it is susceptible to physical damage due solely to handling. So next we have the ability to hold center thickness tolerance. So this is another big risk, and it is right up there with the risk of fracturing. And whenever we say ability to hold center thickness tolerance, I should be a little more specific and say the ability to hold very tight center thickness tolerances. And by tight, I generally mean tighter than, say, plus or minus 50 microns. The reason that this is so difficult is because, again, the materials are very soft and they have a very low abrasion resistance. Therefore, during the polishing process, the polisher removes a very large amount of material very quickly. So unfortunately, even though we wish it was, polishing is not as deterministic as you may think. The polishing process is both a chemical and mechanical process, and the chemical portion definitely is affected by a significant number of environmental factors that, regardless of how well us manufacturers attempt to control them, they will vary slightly over time, and that can be either by the day, by the week, or potentially by the hour. So definitely we can see, and we do see quite often, that you can put a part in the polisher, especially one of these materials, and you can run a polishing run for a duration of, say, 5 minutes at a specific pressure and stroke. And say you may remove 20 microns during that polishing run, but then you could come back and do that exact same run over again and potentially remove 35 microns during the second polishing run. So for this reason, it can become exceptionally difficult to hold pretty tight center thickness tolerances. And this definitely will significantly increase fallout percentages during manufacturing. So as we said, the high-risk process for CT out of tolerance is second side polish. Lastly, we have the uncertainty caused by variations in form. And what I'm getting at here is the metrology and correction uncertainty that we can have. So again, because these materials are so high expansion, during the polishing process, heat will be induced and it will be absorbed into the surface of the part. This heat will again lead to a non-uniform expansion throughout the surface. So this non-uniform expansion will deform the surface from what you would expect when the part reaches equilibrium at room temperature. So therefore, it makes measurement and corrections very difficult. If the part is measured as soon as it comes off of the polisher, it is not a true form to what you would see at the room temperature equilibrium, and you can actually watch it change over time as the part cools down. So, in an ideal world, the best way to manufacture these parts would be to run all of them in the polisher, then let all of them sit until they have all reached thermal equilibrium back at room temperature, then measure all of them and make your corrections. But unfortunately, we do not live in an ideal world, and we understand that all of you designers want your optics and you want them as quickly as possible. And in our case, we have a lot of optics to manufacture and we have a lot of deadlines we have to meet. So we generally will have to make corrections based off of some assumptions. Those assumptions being, based on the surface we are seeing at this elevated temperature, and based on the geometry of the part, how much we need to correct in what area in order to bring that surface into tolerance when it does reach thermal equilibrium back to room temperature. So the high risk processes for variation in form, again, are polishing and the metrology process. So now that we've discussed these risks and challenges, let's discuss how they can affect your cost and timeline. So the good news that we'll give you first is that generally speaking, the materials, like I said, that we would focus on in this presentation are all readily available. They all have a pretty high melt frequency, so it's definitely not something that you generally have to wait a significant amount of time for one of the material manufacturers to get this material in stock or perform a new melt. The downside is, although it is readily available, it is quite expensive, or the material cost is quite expensive relative to, say, an MBK7 or an SBSL7, which is just kind of the general reference that is always used. So we will normally see anywhere from 10x to 20x the price of an MBK7 or SBSL7 blank of a reasonable size or a normal size. In certain cases, if the size exceeds, say, in the realm of 80 millimeters to 100 millimeters, the blanks can become exceptionally expensive, and we can see material prices upwards of 20x plus of MBK7 or SBSL7. So along with the additional expense of the raw material itself, I would also like to mention and most definitely emphasize that as an optical designer, you should expect that if you do elect to use these types of materials in your optical system design, optical manufacturers will most definitely add in an additional expense, and I will say sometimes a rather considerable additional expense to the finished price of your optic that is due solely to pricing the amount of risk involved in these optics. As manufacturers, whenever we commit to making these optics for you, in some cases we're really putting our neck on the line. As we said, these materials and working with these materials can be very volatile. For that reason, even if we do everything right on our end to try to mitigate as many of these risks as possible, we can still experience a failure. And if we do, it's now our responsibility to procure more material for you at our cost and do everything in our power to attempt to deliver those materials on the originally agreed upon date. So there's a lot of risk involved on our end, and unfortunately we do have to add that into the price in the case that something bad does happen. So moving on, with regard to timeline, there are quite a few things when it comes to manufacturing with these materials that can add a pretty considerable amount of processing time. In polishing, this is one of the areas where we see a rather large and consistent increase in time. As we said previously, because these materials are so soft, they have such a low abrasion resistance, they load up the polishing pads really bad. And this basically makes our operators continually recut the polishers to remove that material from the pad. They can continually see issues with surface due to these pads loading up. So they have to use a lot of tricks and take a lot of additional time to make sure they keep those pads cleaned out so that we get a good surface on your parts. With regard to coating, as we previously discussed, there is an additional amount of time necessary at both the beginning and end of the coating process because the temperature in the coating chamber has to be raised and lowered very slowly in order to keep from shocking the parts thermally so that they do not fracture. And then with these materials, there is a pretty substantial amount of time that may have to be involved with rework. So just for some examples, like we had said previously, these materials are very difficult to perform metrology on because they are so heat sensitive and the form changes with heat. So potentially one of our operators may measure one of these parts on the shop floor as soon as it comes off the polisher, and at that point it measures within spec. But then these parts may be measured again later on in process, and at that point be at a more thermal equilibrium with room temperature than they were before. And in this case, they might read slightly out of spec, so we will have to go back and repolish those parts. And then also, like we had said before, because these parts have such a low abrasion resistance, they can definitely come off the polisher and the surfaces look near pristine. But then later on in process, inspection deemed that they have all been scratched or abraded, and we have to go back and repolish. So definitely quite a bit of potential for additional processing time spent for rework with these materials as well. So now that we've discussed all of these potential risks and discussed how these risks can potentially affect your project cost and timeline, we can kind of start going over how we would address these risks logically. So I'll start out here with most definitely the simplest solution to this problem is to not use these materials. And when I say that, that has a big asterisk on it, that as manufacturers, we understand that designers really need these materials. We know that these materials do a lot, especially in terms of color correction, that a lot of other more tame materials do not. So for that reason, definitely in certain situations, they are necessary, and we do understand that. But most definitely, like I said, the simplest way to reduce this risk is to not use these materials unless you absolutely must. And I just really want to stress here that in this situation, what we see a lot with RFQs is that we will have customers send in an optical system that they have let ZMAX or their specific optical design software kind of go through and select some of the materials for them in order to meet some of the constraints they have placed on the system. And in a lot of those situations, that optical design software may select that several of those materials be these fluorides or other high expansion materials because that is the simplest and easiest way for the optical design software to meet those constraints. But it doesn't necessarily mean that those materials are necessary. They may be able to be substituted with other materials, and it may slightly complicate a few other parameters of the system, but in turn, it could make the system considerably more manufacturable if you were able to change those materials. So the main thing we're asking for here is just please do not take everything you get out of your design software at face value. Please be critical of it, based on all these risks that I have now discussed regarding these materials, that if the optical design system tells you to use these materials, it might be in your best interest and definitely in our best interest if you would go through and try some different materials and see how different the performance may be. If it's only a marginal decrease in performance using a more tame material, it may be a rather considerable increase in the manufacturability of the system. So mainly here, if you do go through your optical design software, it does tell you to use these materials and you do evaluate that they are necessary in your system. Just please have realistic expectations for us as manufacturers regarding the size and shape of the optics, the surface quality you desire, the center thickness tolerance, and the form error. So now we can kind of start talking about some design methodologies that can be used to reduce some of these risks. And we'll start off with reducing the risk of fracturing. So with regard to reducing the risk of fracturing, it's generally best practice to select the high expansion materials for the smaller elements in your system if possible. And most definitely, the smaller the better. So you can see on this slide that I have purposely mentioned to try to keep diameters below 50 millimeters to 60 millimeters. I want to explain this a little more, and what I mean when I say that is there's no hard line there that basically says if you select a fluoride or high expansion material that is above 60 millimeters, we will not be able to manufacture it. But as long as it's below 60 millimeters in diameter, we can definitely manufacture it. You know, that is in no way the case. That's no way what I'm trying to say. What I'm getting at there is that's kind of the turnover point where when you have diameters smaller than 50 to 60 millimeters, the process is still in some way slightly forgiving of certain parameters such as geometry. So you can have more non-ideal geometries and still be able to manufacture them without an extreme risk of fracturing. But if you do exceed 60 millimeters in diameter, it becomes a situation where the geometry of the part has to be near ideal for us to be able to manufacture at that size. So like I said, that's not a hard line. Please don't interpret it as such. It's just kind of a general rule of thumb. So the next thing you can do to reduce the risk of fracturing is to use shapes which promote uniform expansion throughout the entirety of the optic. Like I have mentioned previously, you know, the main issue that will cause fracturing in an optic is when you have non-uniform expansion, which causes internal strain, and that internal strain can cause the optic to fracture. So definitely the way to reduce or promote this uniform expansion is to keep the center thickness to edge thickness ratio as close to 1 as possible. So you can see down at the bottom I've included some shapes to avoid. So, you know, please try to stay away from optics which are very thick in the center and very thin at the edge, or vice versa. Try to keep the thickness of the optic fairly uniform over the entire radial distance of the optic. We also ask that you use at least one shallow radii on your optic so that it does not have to be blocked on the second side. Most definitely, if you can use 2 shallow radii, and in this instant, by shallow radii, I am referring to a radius that is lower than 60 degrees in total included angle. So most definitely, if you elect to use 2 shallow radii, it's better on our end because we do not have to block on first side or second side. But most definitely, please use at least 1 so that we do not have to block the optic on the second surface. As we said previously, whenever we block the optic, we have to take the optic at room temperature and place it in contact with a hot tool and hot pitch that is touching the optic localized to the diameter. So it will lead to a significant amount of expansion at the diameter, but not necessarily in the center of the part, which will definitely induce strain and could cause fracturing. I would also like to mention at this point that here at LaCroix, we do use some proprietary polishing, coating, and cleaning methods in order to keep the heat generation down when we are working with these materials. You know, we're going to do everything in our power and best practice to get you the highest possibility of us being able to manufacture these materials with minimal issues. So moving on, we have reducing the risk of staining. One thing that you will see here and you will continue to see as a recurring theme throughout the remainder of this presentation is that minimizing diameter or aperture size, generally speaking, helps to reduce almost all of the risk that we had previously discussed with these materials. So here with the risk of staining, you know, statistically speaking, with regard to aperture size, the larger the aperture size of the part, the more surface area that's available on the part. So for that reason, there's a higher chance of stain relative to a part with a smaller aperture size that has a smaller amount of surface area. So we definitely recommend that you minimize those diameters and apertures as small as possible. We ask that you specify a coating to be applied to the optic. So generally speaking, the coating is very dense and it helps the optic to be more environmentally stable. Like I said previously, in the case of our long-term storage, we do have optics, if they are uncoated, that may sit in the warehouse, and if they reach elevated levels of temperature and humidity, they can form stain. Most definitely, that coating helps to provide an environmental barrier against that humidity, so it will help with regard to the staining aspect. And then also in the use of the optic, so we recommend that if you do select these materials, that you use the optic in a temperature, humidity, chemical controlled environment. But if you do have a coating applied to the optic, it can also kind of shield the surface of the optic from certain chemicals if it does come into contact with those. Then again, as another recurring theme here, you will see we also request again that you use at least one shallow radius, again a radius that's 60 degrees and included angle or lower, so that the optic does not have to be blocked on the second surface. Like we said previously, during the blocking operation, you have a polished surface that comes in contact with the blocking pitch, which has certain chemicals that do not react well with the surface of the optic. So if you can keep that second surface from having to be blocked, the better. Moving on, we have reducing the risk of physical damage or poor surface. So most definitely, this is a risk which becomes very difficult to reduce in its entirety. But you'll see that, again, one of the recurring themes was to minimize that diameter aperture size, again. So the smaller the aperture size, the less surface area that you have available, so the less chance of having a scratch or abrasion on that optic. And then also, generally speaking, if you have a smaller diameter or aperture size, the total weight of the optic is less relative to an optic that has a larger diameter or aperture size. As we had mentioned previously, so during a lot of these operations, these optics have to be transported from one area to another, and when they are transported, they have to be placed in a tray. For a very heavy optic out of these materials, these very soft, low abrasion resistant materials, if that heavy optic is placed with a convex surface down in the tray, there's definitely a lot of weight that is all focused on the vertex of that optic. So if you can reduce the weight applied to that vertex, the better. And then you will see on the next point here, I've also mentioned to design with a shape that uses a concave or a shallow convex radius for the same reason, that if you do use a concave radius, we always have the ability to place that surface down in the transportation trays. So you do not have any point of the surface that is physically in contact with the tray. You're just contacting right on the edge, which is outside the clear aperture. Or we also, would like you to use a very shallow convex radius so that you do kind of spread out the area that weight of the optic is distributed over. You don't want all that weight right on the vertex of the optic. Many times over the years we have seen that with many parts out of these SFPL materials, you will see issues directly on the vertex that was due to how they were placed in the processing trays. Along with reducing the risk of physical damage or poor surface, I would also like to mention and stress that, as we have said, these materials, we really struggle with how bad they load up polishing pads. And because they do load up polishing pads so badly, it becomes very difficult with these materials to achieve a good surface while also simultaneously achieving the center thickness tolerance that you have requested and the surface form tolerance that you have requested. So with these materials, many times we will get to the point that we have good surface form and we meet your center thickness tolerance, but the surface is not ideal. And by ideal, I just mean, it's not perfect. It's not a 10-5 surface. But many times, we run the risk of, if we do attempt to polish that surface one more time to remove some of those surface errors, some of that physical damage, those scratches and digs, that we run the risk of running the optic under on CT. And many times for us, we would rather keep the slightly poorer surface quality if it does meet the spec that you have provided, and stick with the current center thickness tolerance that is within spec, than we would trying to attempt to run it one more time and potentially run them under on CT. When we do run parts under on CT, there's nothing we can do to repair them. There is no longer enough material left to repair and meet the finished spec that you have provided. So at that point, those optics are totally scrapped. And in this case, it's really important to us that designers understand with these materials, reaching 2010 and 10.5 on the surface quality can be appreciably difficult. On any part of any relative size, most definitely 60-40 or 80-50 is preferable for these parts. For very small parts, parts that may be 30 millimeters in diameter, 20 millimeters in diameter or less, we can sometimes sign up for 40-20 on these parts, but very seldom, just due to this nature of how they load up polishing pads, how difficult it is to achieve that good surface while simultaneously getting the form tolerance and center thickness tolerance where you want. It's very, very difficult for us to quote 2010 or 10.5 on optics using these types of materials. So as for reducing the risk of CT under tolerance, again, you will see that we request you use at least one shallow radius so the optic does not have to be blocked on the second surface. So if the optic does have to be blocked on the second surface, you cannot remove the optic from the blocker in order to measure the center thickness, because if you do have to put it back on the blocker and repolish that surface for any reason, you cannot get it back in the exact same spot, and it can lead to a few other issues. So we really want to keep it blocked. But in that case, we have to indirectly measure the center thickness. If you do not have to block the optic second side, we can run it in our CNC processes. And in our CNC processes, you can remove the optic from the machine between each polishing run in order to directly measure the center thickness. So that is always preferred when attempting to hold tight center thickness tolerances using these types of materials. We also ask that you loosen the form tolerances to the maximum extent possible. Like I said previously, with these materials, we're not just trying to hold each of these tolerances individually. You're trying to make all of them happen at the same time. So, meet the surface quality, the CT, and the form all together. And most definitely, on your form tolerances, if you have an extremely tight form tolerance, we can have that issue, like I said previously, where we're, setting in a good spot on the CT, but we're just barely out on the form tolerance, and we do have to make another polishing run, and, we can make that run and all of a sudden run all of the parts under on CT. And at that point, like I said previously, those parts are completely scrapped for us and we have to source new material. So most definitely, please allow as much tolerance as possible for the form. I understand, the software gives you a specific form tolerance that you need to hit, but when I ask for this, I mainly am asking with regard to the safety factor. On materials that are tamer than the fluorides or high expansion materials that we have been discussing, most definitely a larger safety factor on the end of the designer is still potentially reasonable for manufacturing. But please try to keep that safety factor as small as allowable for these types of materials. Just please try to give us as much form tolerance as available in the system. So I would also just like to mention that, please understand from our end, because these materials are so soft, they do abrade so quickly, like the surface quality, it is just very difficult for us in general to attempt to hold center thickness tolerances tighter than plus or minus 50 microns for these types of materials. Again, we have to meet all three, the surface quality, the CT, and the form tolerances all at the same time. And it's very difficult to do all of that simultaneously, and just achieving plus or minus 25 micron, plus or minus 20 micron center thickness tolerances with these types of materials is just a little unreasonable on our end. And so lastly, we have minimizing the uncertainty due to variation in form. So this is a pretty simple one, and basically what we ask is that you just design using stable shapes. So generally speaking, more stable shapes are again those that have a smaller diameter. Please try to reduce those aperture sizes. Stable shapes generally have larger CTs. And then we request that you stay away from meniscus lenses. We have severe metrology concern using high expansion materials with meniscus lenses. They deform rather appreciably. And we also ask that you stay away from very, very thin parts. So most definitely try to keep the thickness as large as possible. Again, with that very, very small center thickness, these parts can very easily deform, and it makes the metrology extremely difficult. So like we had said previously with the form tolerances, or the center thickness tolerance, please allow us as much irregularity in surface form tolerances as possible. Please do not spec it any more than necessary. We understand that as designers, you do like to have your safety factors designed into the system. But that little safety factor on your end, potentially that double safety factor on your end, can triple or quadruple the amount of processing time and effort and risk on the end of your manufacturer. So please allow, the maximum that your system can tolerate directly to your manufacturer. So to kind of start wrapping everything up here, I just kind of like to again go over some general design or tolerancing guidelines. We pretty much discussed all these at this point, but I'll just go over and reiterate them one more time. So again, try to keep those diameters as small as possible, but most definitely smaller than the 50 millimeter to 60 millimeter range is best on our end. Try to use those stable shapes that have a edge thickness to center thickness ratio very, very close to 1. If at all possible, please use at least one shallow radius, which again is a radius smaller than 60 degrees in total included angle. If you do have the option, please use 2 radii that are smaller than 60 degrees in included angle, but most definitely please try to use 1. With surface quality tolerances, please do not expect us to really bid anything that is tighter than 40-20. Most definitely as the aperture size increases, we need to increase that tolerance. So definitely on larger optics, 60-40 or 80-50 is ideal on our end. With CT tolerances, please do not go any tighter than plus or minus 50 micron. And again, just please allow the maximum that your system can tolerate. And then also, please allow the largest form tolerances that your system can tolerate. So in conclusion, with regard to designing for manufacturability using fluorides and other high expansion materials, your best option for these materials with regard to the least amount of risk and then the least amount of additional cost and timeline added to your order is to not select these materials in your design if you can design with a tamer material, if it does not add an appreciable amount of complication to the design itself. But if you do deem that you need these materials, most definitely us as manufacturers do realize that they are in some situations necessary. But if you do deem you need these materials, please just understand they will always demand a premium. But if you do follow the suggestions that I've outlined in this presentation, that will get you the least expensive prices and the best timeline possible for your design using these types of materials. So that's everything that I have for you today. If you do have any additional questions, please feel free to send me an email or give me a call here at LaCroix Precision Optics. I've included my email address and my phone number below. If you do have any specific project where you're wanting to use these materials and you have some specific questions potentially about the manufacturability of certain elements, I'll be happy to take a look at your drawings and give you some feedback. I believe that's everything I have, so I very much appreciate all of your time. You all have a great rest of your day.